rewrite it here. With the same symbols, so ET is equal to 1 minus Cmax divided by beta k plus 1 minus Wt divided by Cmax beta k plus 1 that multiplies APT. Okay, so let me explain this relationship here. What is Cmax divided beta k plus 1? It's Wmax. And therefore, at the numerator here, you have the difference between Wmax and Wt. So it's the gap from current storage to saturation. At the denominator, you have Wmax. You can easily check that when Wt is equal to Wmax, Et is equal to EPT, and when Wt is equal to 0, Et is equal to 0. You can easily check it. What should I do with this estimate of evapotranspiration? Actual evapotranspiration. What should I do? I should take into account that this is water lost from where? From the storage into the catchment. So when I apply my model at each computational time step, conventionally at the end, after having computed year 1 and year 2, I should subtract from Wt the actual evapotranspiration Et by checking that Wt doesn't become negative. So there must be a constraint. So again, at the end of my computational time step, I subtract evapotranspiration from the storage Wt into the catchment. And if the storage becomes negative, then I equate it to 0. This allows me to take into account also the evolution of the catchment during interstorm periods. It doesn't rain. It's clear that the storage into the catchment goes down. It goes down because there is evapotranspiration. Of course, you may say that storage may go down also for other processes like deep percolation. We don't take them into account. This is a simple model. Okay, now the model, the theory is clear. And I am sure it's clear. Let's say that the theory is there. I am sure that it's not yet clear in your minds because you need some time to digest it. What I suggest is the following course of actions. And I'm planning to make an exercise on IMOD, not tomorrow. Tomorrow I would like to move forward with the theory. Next Tuesday, we will make an exercise. I suggest that before making the exercise, you have a look at what we discussed. You may have some open questions, then let's make the exercise. After the exercise, if my prediction is correct, it should become very clear to you how the model is structured and how it works. And you should find it quite simple. The only problem here is to remember how to compute the integral that we computed last time. Once that you can compute that integral, the rest of the theoretical treatment, it's easy. It's also easy to remember. But if after the exercise there is something that it's not clear to you, if after the exercise you feel that it's very complicated, it means that something went wrong, probably in my explanation. I'm not saying that it's a problem with the a unique causal explanation. It may be that my explanation was not clear, also because a couple of weeks passed from introduction to conclusion, and then let's discuss again. If you still think that it's really tough, something went wrong. So let's discuss again. But let's postpone this discussion after next Tuesday, okay? And meanwhile, I didn't finish yet. Meanwhile, please have a look at the web pages, and everything should be quite clear. Okay, let me conclude by saying one thing. How many parameters does this model count? Let me make a list. And let me put this sketch here. So, beta k, number 1, number 2, Cmax, number 3, alpha, number 4, kq, number 5, ks. Beta k is the exponent in the analytical relationship giving the percentage of saturated area. Cmax is the maximum storage in the most permeable, let me use this term, location of the catchment. Alpha is the weight that splits runoff in two components. Kq is the constant of the series of 3 reservoirs. Ks is the constant of the linear reservoir that is placed here. Remember the units. Cmax is a length, beta k is adimensional, alpha is adimensional, kq it's a time, ks it's a time. Be careful, sometimes there are formulations for the linear reservoir where kq is the inverse of what is depicted here. So the unit may be 1 over time. Be careful of that. So when you write an algorithm or you use an algorithm, try to check whether the storage in the linear reservoir is written in this way, k times qt, or it's written in this way, qt divided by k. This is the storage-discharge relationship in the linear reservoir model that we treated a couple of weeks ago, 3 weeks ago. Be careful on how k is defined. Okay, I will try to stick on defining k as a time constant, but I don't remember actually my algorithm, which I took from the web, what kind of assumption makes. We will have to check. 5 parameters means that if you compare IMOD with the linear reservoir, which has only 1, you understand that the model is more complicated, but on the other hand, more flexible. These parameters need to be estimated. How? We will discuss, I don't think maybe also tomorrow, about techniques for finding the best values for model parameters, whatever model we consider. And these techniques are called model calibration. There are several synonyms like model optimization, model parameterization, model estimation. I will use model calibration because we calibrate the parameters, but you are free to use whatever any of the synonyms that I mentioned. Okay, for today I think it's better if I stop here. Tomorrow I will introduce groundwater models, because so far we spoke about models for simulating surface runoff, surface flow, river flow. But as I mentioned to you, groundwater is another essential, very important source of water, and therefore we have to say something also about groundwater models. That's tomorrow. Thank you.